what we're going to start talking about with a really, really stupid example at first. But the example will be sufficiently stupid that it'll be really obvious what's going on. Okay, and then we can, make the examples not stupid. Okay, so let me just sketch a graph, okay? And so I'll have y, I'll have x, and just for sake of demonstration, I'm going to pick a really boring function. Okay, I'm going to pick the function y equals 1. Not a particularly interesting function, is it? But what I'm going to do is I'm going to say, all right, pick some point t along the x-axis. Okay? So here's what I'd like to ask. What do you think, well, here, let me write it this way. Okay, can I define a function like this? Okay, so I'm going to define a function of t that's going to be the integral from 0 to t of whatever my function is. In this case, my function f is just the quantity, the constant 1, which is not all that interesting. But in general, it could be more spicy. Okay, so first off, does this feel weird, the way I've defined this function? Does it feel strange? Do you think I'm like pulling one over on you guys? No? It's too early in the morning to make that judgment? Okay, well, what the heck does this thing mean in my particular case? So let me just ask this. What is a of 0? Okay, why? Right, so this would be the integral from 0 to 0 of 1 dx. So what is from 0 to 0, what's the width of the interval that I'm dealing with? Nothing. And so what's the area enclosed? Also nothing. Okay, that one's easy. What's a of 1? Well, it'd be the integral from 0 to 1 of 1 dx. And because we're not boneheads, well, maybe we're temporarily in the state of being a bonehead because it's 8 in the morning. All right, what would that be? Okay, well, what does the integral from 0 to 1 of f of x here mean? Like, what's the meaning of it? It's an integral, so I even use the big letter A. Yeah, the space enclosed, the area enclosed. Okay, which is what? From 0 to 1? Right. All right, why 1? Because, so what shape is this integral represent? 1 unit this way, and the function's 1 unit tall, so the total area is 1. Right? Okay, so that's good. Okay, so let me sketch this one in purple. This would be 1 unit here, 1 unit up. It'd be that stuff. Okay? All right. Now, if we continue this game, what's a of 2? Two. Okay? And so on. Right? Okay, makes sense? Okay, so when I say and so on, what do you think our formula for a of t would be if it's 0, 1, 2, what would a of 3 be? Probably guess. 3. All right, so do you think this is correct? So what's A? If I plug 0 into this, what do I get? If I plug 1 into it, I get. If I plug 2 into it, I get. That's interesting. Okay. Then I could ask the following. What is the derivative of A of t? Well, okay, so I've got this function that describes how the area grows as I sweep towards the right. In this case, it's linear because the original function was constant. So what's the derivative of A of t in this case? Well, what was A of t? In this particular example, it worked out to be t. What's the derivative of that? 1, thank you. So derivative with respect to t, right? Okay. It's 1. Well, does 1 seem like a thing we've seen before? We've seen this before. Where have we seen it? Right there. It was the function that we were integrating. Okay? All right, so does that kind of seem interesting? This calls for further investigation. Yes? Okay, let's do an example that's not quite so stupid. Okay, so this one was stupid insofar as the function being a constant is not all that interesting. Okay, so what's maybe one beat up spice level up from being a constant? Okay, something linear. Okay, so let's just use x. That seems like a good example. Okay, so we just did the, I don't know, what's the very bottom spice level at B-dubs? What's the, like teriyaki or honey barbecue? Yeah, barbecue's got at least a little spice in it, but yeah, we're gonna go up to like, oh, I don't know where, huh? Yeah, because it's got garlic in it, I guess. Right? Okay, so let's take our next example. All right, and let me just use y equals x. Okay, so again, I'm thinking of t as being an unknown number on the x-axis. Okay, it could be small, it could be big, whatever. And then I'm going to define a of t to be the integral from 0 to t of our function, which is in this case x, dx. Okay, so like before, let's ask, what is a of 0? This one, like before, works out to what? A of 0 is 0, right? The integral from 0 to 0, we're not actually enclosing anything, okay? All right, so that one's the same, but what about these other ones? A of 1 would be this. Okay, now geometrically, what would that be on my picture? This would be the blue area. Okay, what is the blue area geometrically? Like, not forget the number, but what shape are we dealing with? Right triangle, right? Base, what? Height? Area? So the area is a half, yes? Okay. Oops. It's always fascinated me, like, why do you say 0.5 instead of 1/2? I guess, right? Pesky decimals. Huh? Yeah, well, that's been a problem for many years. Did I tell you guys about the A&W root beer 1/3 pound hamburger story? Yeah. Huh? It's pretty sad. Yeah. Then 1/2 because, yeah. Or 1/4 because 3 is smaller than 4. Yeah. Yeah. Welcome to America. Yeah. But do you go to McDonald's and I'd like a 0.25 pounder with cheese? No? Well, okay, but yeah. You know where you definitely can't do that, though? In France. Because they own the metric system of some, right? The Pulp Fiction. Okay, just, yeah, yeah. Okay, have to have some fun. All right, so that's A of 1. What's A of 2? Okay, what would the base be? Well, we're still talking about a triangle, right? We'd just be talking about a bigger one, right? Base what, height what? 2, 2, and so the area is 2, right? Okay. All right, what's A of 3? Base 3, height 3. Thank you. 9/2. Okay, or 4.5. There you go. Okay, and let's just do one more. What's A of 4? Base 4, height 4 would be over 2, which would be 8, right? Okay, good. Okay, so here the area function is a little bit more interesting because it's not linear, right, like the last one was. So can we kind of use our thinking caps here and come up with what's a formula for A of t based on the numbers that we've crunched? Okay. Yeah, let's try that. Does that work? Well, check it. If you plug 0 in, do we still get 0? Yeah, okay, so that one's good. What about 1? 1/2, 2, 2, 3, 9/2, 4, 8. Do we think we've got it? That's interesting. Okay. Furthermore, what would A prime of t be? Just t. Huh. That's interesting. Have we seen just t before? Or just x before? Yeah. Okay, so let's think of it this way. Think of x and think of t squared over 2. Okay, so, or just maybe for the sake of right this instant, think of x and think of x squared over 2. What's the relationship between those two functions? One of them is the derivative of the other, right? X is the derivative of x squared over 2. Or another way to say that would be x squared over 2 is the antiderivative of x, right? It goes either way. So what do you think we've noticed here, guys? This area function has something to do with antiderivatives. Well, that's surprising. Well, unless the story's been spoiled already for you, but because you've seen this before. So here's sort of the point, right? When we started talking about integrals, we were thinking purely about area, right? We also talked about antiderivatives. Is there any suspicion that those two things might have anything to do with each other? Like if we were just, if this was 300 years ago and we were we're Newton, we're sitting with Newton under the apple tree, okay, which, by the way, that story is apocryphal, but whatever. We're sitting with Newton at Woolsthorpe, and we'd be like, okay, we figured out this idea of antiderivatives. We've also figured this idea out about area. is there any reason necessarily in advance to guess that the two have anything whatsoever to do with each other? No. Why would they? But what have we just discovered? In fact, they do have something to do with each other. And that is the fundamental theorem of calculus, is that they are actually connected together. Okay? All right, so let's say it this way. Oops. FTOC. Okay, there are actually two parts to the fundamental theorem. Okay, so let's talk the first one. The first one is, well, if you have a definite integral, okay, that's what we were trying to cook up, right? Then what you can do is you can find an antiderivative of the thing, and then just plug in the two numbers at the top. Okay? So the whole problem of integrating comes down to finding the antiderivative. Okay, this explains, let me just write it. Okay, this explains why we use the same symbol, the little S thingy, for both talking about integrals where there's numbers at the top and bottom, which represent signed areas, or net signed areas, and integrals where there's not numbers at the top and bottom, which represent antiderivatives. Okay, we picked the notation because we had already, okay, when I say we, I mean sort of the royal we of mathematicians of the world, okay? So what I mean is, we stumbled upon this stuff. We said, oh, this area function has something to do with antiderivatives. Okay, so why don't we use a common notation for the two of them? Because they're related to each other. Doesn't that seem reasonable? Yeah? Okay, so from that perspective, or maybe from y'all's perspective, it looks like I've put the cart before the horse by picking two notations that look similar, but I haven't told you how they were related together until right now. Okay, is that all right? Okay. Huh?
What are we talking
about? Okay, yeah, maybe I'm being a little bit too philosophical here. Okay, so, all right. What was the notation we used for antiderivatives? To mean, hey bro, take the antiderivative of f. We picked this symbol, right? Yeah. This funny s. But then we also use that funny s to talk about area, right? Why would we pick the same symbol unless the two ideas have something to do with each other? Right? So, like, again, think it's a few hundred years ago in Woolsthorpe, and we've got this idea of antiderivatives and this idea of area. And we haven't figured out that they have anything to do with each other. But then we do, and we're like, brilliant. Let's pick a notation that expresses that similarity, or that relationship. And so we did, and it's this dude, right, the integral symbol. Okay, actually that one was, we wouldn't be in Woolsthorpe with Newton, we'd be in, on the continent with Leibniz, because he came up with that, the integral symbol. All right, whatever. So I guess what I'm just trying to say is, from a student perspective, it might seem like, wait a minute, how do these things have anything to do with each other? But it's today where you find out that they do. Okay, is that kind of all right? Yeah, okay. So anyway, good. So let's return to our original problems, and let's do them with this sort of new knowledge. Okay, so the first example was this, right? And the function I defined was this. Or, sorry, it was the first one I did was 1. Okay. And we noticed that after crunching a few examples, that A of t was t. Okay, so that's what we got when we just kind of thought it through. But here's how we would have gotten it the other way. What is the antiderivative of 1? X. Okay. Now, could I have written a plus c there? Should I have written a plus c there? Okay. Technically, yes, but in this particular case, we'll see in a minute why it's not necessary. Okay, so let me just write that. Okay. All right. So what I'm going to do, let me define a new notation. Okay, so this vertical bar, okay, is going to mean plug in the thing at the top for x, you get something. Plug in the thing at the bottom for x, you get something else. Subtract the second answer from the first one. Okay, so in this case, what we would get is t plus c minus 0 plus, that is the worst looking c ever. This. Okay, so what did I do? Everywhere I saw an x, I plugged in the thing at the top. That got me t plus c. Then for the 0, everywhere I saw an x, I plugged in the 0. I got 0 plus c. And then I'm telling you to subtract the 2. Okay? Now, can we simplify this a bit? Yeah, and in particular, what happens to the c's? They cancel. And that always happens when we're doing this definite integral thing. So I don't have to write it in the first place because it's just going to cancel anyway. Okay, okay, so is that cool? Oui ou non? Oui? Très bien. Okay. Now, the other thing that I could ask is what is a prime of t? Well, we know what a of t is, so what's a prime? 1. That's just, how do I know it's going to be 1? Well, what was the function that I was integrating? That's interesting. Okay. All right. Ready for a spicier one? Let's do, actually, I got to show you guys this. This is really cool. All right, so let me take y equals 1 minus x squared. Okay, and let me just sketch that. Oh, yeah, sure. In fact, I'm going to go grab a water and those sheets now that the copier's done, so I'll be right back. While you guys are meditating. Okay, we Gucci? All right. Make sure the audio is still good. Yeah, I think we're good. Okay, so I'm going to take y equals square root of 1 minus x squared. Okay, what shape is this, other than my horrible drawing? Huh? No, did I say square root? Sorry, didn't mean that. If I had said square root, then it would have been a semicircle, but it's not. What is it instead? Yeah, upside down parabola. Okay, great. So what I want to know is, what's the area inside that thing? Good question. Right? Okay, so this one's a little tougher. Because do we know any obvious geometry that's going to save us here? No. Okay. In the last two examples, when we were doing, we had a horizontal line and a straight line, the segments of area that we were adding up were either squares or rectangles or right triangles, both of which were easy from a geometric perspective, right? Okay, so that was good. But this is like parabola-y stuff. Do I have any idea what to do with that? Nope. Okay, but most people in the math department don't even know this. There's a buddy of mine named Archimedes. You guys heard about this guy? And no, he wasn't, well, he was, but he's not just the owl that was in The Sword in the Stone, the Disney version. You guys ever watch that when you were little kids? Yeah, okay. Not just that dude. Ancient Greek mathematician, lived in Syracuse, died at the hands of the Romans in the Second Punic Wars. Huh? No. In Sicily. The OG Syracuse. Okay. No, basketball hadn't been invented yet, honey. Yeah, anyway, died at the hands of the Romans during the Second Punic Wars, etc. Okay, so he actually figured out how to deal with parabolas, and this is super clever. All right, so what I'm going to do is I'm going to draw in this triangle, okay? So I've inscribed a triangle whose base is the same as the base of the parabola, and whose third point is the same as the vertex of the parabola, okay? Now, clearly, what's the area inside the parabola? It's bigger than the area in the blue triangle, right? That's not at all in question. The question is, though, what's the relationship between them? Okay, and this is where it gets really cool. All right, so let me switch gears for a second. Let's go back to the playground at your elementary school. Okay, did you guys have a seesaw? Or are those not okay anymore? Yeah, okay. So, under what conditions are two kids on either end of the seesaw going to balance? When they weigh the same, okay? Why? Because what's the distance from the hinge of the seesaw to either end? It's the same number, right? If you put the hinge here, right, you're probably not going to get the contracts for the seesaw company, right? It's too bad, though, because we could teach our kids physics if we did that. All right, so I seem to remember doing this when I was a kid, where you put one kindergartner here, and then a fifth grader here. Not at the end, but sort of partway along the beam. And if he slides closer to the end, he'll overbalance. And if he slides closer to the hinge, he'll underbalance. But there's a certain point in there where it's just right, where you can get a bigger thing to be balanced by a smaller thing. So, did you guys ever do this? Well, that works too, right? Right, so you guys were doing physics. And furthermore, you discovered the law of the lever. Okay, so here's the law of the lever. If I have distances d1 and d2, and masses m1 and m2, what's the relationship? d1 is to d2 in the inverse ratio of the masses. Okay, so the idea here is if I've got, say, the fifth grader who weighs twice as much as the kindergartner, okay, the ratio of their masses is 2 to 1. What should the ratio of their distances be? 1 to 2, the opposite. And that's why you have to put the fifth grader closer to the fulcrum and the kindergartner further away. Okay, does that kind of make sense? They're backwards of each other. Yeah? Okay. Well, Archimedes, not just being a crafty mathematician, was also what we might call a crafty physicist. Okay, this is back when math and physics were really the same discipline. They've kind of drifted apart in the intervening years. He said, okay, I understand this law of the lever business. So what I'm going to do is I'm going to think about putting the parabola piece here and the triangle piece here. Okay? And if I can figure out the distances at which they balance, then I've figured out the relationship of their areas or their masses. Right? Solving one problem solves the other one. Does that kind of make sense? His brilliant idea? Okay, so what he did to figure that out was he carved the two things up into little pieces and said, okay, this piece would balance with this piece with this piece, and so on. Okay, but what he figured out, I'll give you the TLDR, is that the distances were in the ratio of 3 to 4. Okay? Now, it makes sense that the parabola would have to be closer to the hinge, right? Because the parabola's got more stuff in it. That's obvious. What's not obvious is what the distances come out to be. It comes out to be 3 to 4. All right, given that, if it's 3 to 4, what's the ratio of the masses, or therefore the ratio of the areas? 4 to 3, okay? And so a way that we could say this would be is that the parabolic area is 4/3 of its inscribed triangle. Okay? Make sense? All right, let's go back up to our picture. For the particular parabola that I picked, the 1 minus x squared guy, what's the area of that blue triangle? Well, it's right triangle, so that's nice. Or not right triangle, but yes, that's what I meant. Okay. Or I could split it down the middle into 2 right triangles. Okay. So base is 2 units, height is 1 unit. So the area of the triangle is, in this case, just 1 unit. So what's the area of the parabola? 4.3. I'm going to smack you. 4/3. Okay. Does that make sense? 4/3? Okay. So the area of our parabola, so what we've discovered is by, or let me write it this way, sorry. Using this result of Archimedes, we get 4/3. So let's use this modern technique and make sure that we actually do get 4/3, because it would sort of suck if Archimedes was wrong. Yeah? Okay. So Now, actually, what's really interesting is Archimedes gives two completely different versions of a proof of why it's 4/3. The other of which is something that you guys could do with Calc 2 knowledge. He comes up with an infinite series, basically. I mean, this guy was just brilliant. Frickin' Romans. To quote from Monty Python's Life of Brian, right? What have the Romans ever done for us? Well, they built the roads, and the aqueducts, and the baths, and the... Okay. Anyway. So let's double check that Archimedes is right, okay? Because we've got another trick up our sleeve, namely, what's the antiderivative of 1 minus x squared? What's the antiderivative of 1? X. What's the antiderivative of x squared? X cubed over 3. Okay, and then the fundamental theorem says I need to plug in the top number, I need to plug in the bottom number, and I need to subtract the two answers and not botch the arithmetic in the process, hopefully. Okay, so what do I get if I plug in the top number? Well, I get 1 minus 1/3. Okay. What do I get when I plug in the bottom number? Well, here we have to be a little bit more careful. Okay, I get that. Okay, now let's simplify and be careful with the minuses. All right, so I've got a 1 in the front, right? Yes? Okay. I've also got another 1 because I've got minus a negative 1. Okay, so that makes a total of 2 last time I checked. I've got minus a third from right here. Okay, and then the one where we really have to think, what's negative 1 cubed? Negative 1 times another negative is positive, times another negative is negative. So what's all that said and done? Minus a third. And voila. What do we get? 4/3. Our buddy Archimedes was right. Yeah. Well, you probably could have guessed that he was right because I wouldn't have brought him up if he had been wrong. Probably. Although it is worth pointing out that you remember the product rule? Leibniz messed that up at first. He thought it was the product of the derivatives at first. Now he came to understand the error of his ways. Okay, but his first guess turned out to be wrong. That happens. It's all right, as long as you fix it. Okay, so we've kind of talked about here the fundamental theorem, which is well, the two versions of it. We'll continue with this on, let me hand these things out just so you guys have them. We'll continue with this idea on, more on Wednesday. So let's start with what have we defined, what did we do at the very beginning? We defined this area function. And the idea was that the area function was sweeping out or counting up the area up to a certain point, but we made that point a variable so that it would define a function. Okay, and then we kind of figured out what was going on with that. Okay, then the second thing we need to do is figure out how derivatives and integrals play together. Okay, now, what do you kind of think they should play together? They kind of operate like addition and subtraction, that one undoes the other. Okay, but there's a few like footnotes, and the footnotes is what we'll have to deal with on Wednesday. Okay, so does that kind of make sense? The big idea here, roughly? Okay, and like I said, we'll get in more into the weeds on Wednesday. Okay, so when we stop on material for today, but the assessment-y stuff. Okay, so what do I? Have you guys all scheduled something with me? Yeah, not yet. Okay, so you get to pick 2 of the standards. Then you can redo 2 of the standards avec moi per week. Okay, that's doesn't count doing them on the exam. Okay, like so, I think our next assessment is Friday next week. Is that right? Like Monday next week? Oh, is it? I try to avoid that usually. Let me double check the calendar. Okay, and Canvas. And yeah, I really hate putting exams on Mondays for exactly that reason. Pull up Canvas and let's just see if I'm being a bonehead. Well, do you guys not want it to be on Monday? Huh? It doesn't matter to me.
Is it just going to be 2 of the standards?
The assessment?
Not all be more than 2.
Yeah, okay, so yeah, good question, right? On written assessments that you guys do in class, every standard you haven't passed will be on there, okay? For assessments that you come redo in the office, right, it'll be you pick 2 of them that you haven't fully passed yet. Okay, so I sent all of you guys an email yesterday with a screenshot of your part of my giant spreadsheet. Okay, so what you want to do is you want to pick one of the red or yellow items on your sheet, well, 2 of them, okay, that we have actually covered thus far, right? So the assessments we went up through the chain rule was the last one that we've done on a written test, okay? So pick 2 of the red or yellow things up through the chain rule. It's up to you which ones they are. Just tell me, okay, in advance, please. And then when you guys come, that's what you guys will do. Okay, so does that kind of make sense? So let me double check the calendar. I think I may have put it on a Monday because I was trying to keep I didn't want 2 of these to be too close together. And we've also got April to worry about. Okay, but I'll double check the calendar and do something that makes sense. Okay, so are we all clear as to what we're doing? Yeah? Okay. All right, well, I'll quit the stream then. And yeah, when you get the booking form, it did give you a place where you could put in comments. And if you put in there what you wanted to go over, great. If you've already booked and can't do that, just send me an email. And that way I know what you'd like to redo, and so I can think of some problems. Okay? All right, let you guys out a little early today. No complaints there, huh? Yep.